Now look, I want to tell you something today that's going to bother you. And it should bother you because it bothered me for a long time. And I think that's actually a sign that you're paying attention. You're sitting there right now. You feel solid, right? The chair underneath you feels hard. The floor feels firm. You feel substantial, like you're really there. And that feeling, that deep physical certainty that you exist as a real solid thing in a real solid world. I'm going to show you step by step with actual numbers why that feeling is one of the most magnificent lies the universe has ever told you. Let's start small. I mean really small. Everything you've ever touched, every table, every rock, every person you've ever shaken hands with is made of atoms. Now this is the single most important sentence in all of science. I've said this before and I'll say it again. If some catastrophe wiped out all scientific knowledge and I could only pass one sentence to the next generation of human beings, it would be this: all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling when squeezed into one another. That's it. That's the deep secret. And from that one sentence, enormous amounts of the world become understandable. But here's where it gets interesting. Here's where it gets really interesting. What is an atom, actually? Not the cartoon picture you saw in school with the little ball in the middle and the electrons zipping around it in a neat little circle. No, no, no. That picture is, look, it's not wrong in the way that 2 + 2 = 5 is wrong. It's wrong in a more subtle, more beautiful way. Here's the actual situation. You've got a nucleus at the center. Now, the nucleus is unbelievably small, unbelievably. Let me give you an analogy, and I want you to really sit with this one. Imagine you take a hydrogen atom, the simplest atom there is, one proton, one electron, and you blow it up, magnify it, until the nucleus, that single proton, is the size of a marble you can hold in your hand. Now the question is, where is the electron? How big is the atom itself on this scale? The atom is now the size of a football stadium. The marble is sitting there on the 50-yard line, and the electron, this fuzzy, smeared-out wave of probability, is somewhere out near the stands. And between the marble and the stands, nothing. Essentially nothing. No air, no substance, just space. Now, when I say nothing, I have to be a little careful because I'm a physicist, and physicists are very fussy about words. But for the purposes of your intuition, yes, empty, vast, startling, humbling emptiness. And the nucleus takes up roughly 1 part in a quadrillion of the atom's total volume. That number, a quadrillion, is a 1 followed by 15 zeros. The nucleus, which has essentially all of the mass, all of the weight, everything that makes the atom heavy, sits in about 1 part in 10 to the 15th of the total space. So when you're holding a rock in your hand, let's say a rock about the size of your fist, almost all of the volume of that rock is empty space. Almost all of it. The stuff that's actually there, the dense nuclear material that constitutes the mass you feel when you lift it, could fit, all of it, from the entire rock, into a volume you couldn't see with your naked eye. Now you're going to say, well, Feynman, if a rock is mostly empty space, why can't I put my hand through it? And that is a great question. And the answer is quantum mechanics, which is a whole other story. The short version is that the electron clouds of the atoms in your hand and the electron clouds of the atoms in the rock are pushing against each other. Not because they're solid, because of a quantum principle, the Pauli exclusion principle, that prevents electrons from being in the same state at the same time. So what you feel as solidity is actually a quantum mechanical repulsion between electron probability waves. You're not touching the rock. Your electrons and the rock's electrons are refusing to share the same space. And that refusal is what your nervous system interprets as hardness. It's electrical, fundamentally. It's quantum mechanical. It is not at all what it looks like. But here's what I really want to get to today, because we've only just started. We said the atom is mostly empty. Fine. But I want to zoom out now. I want to zoom out past the atom, past the molecule, past the cell, past your body, past the room, past the city, past the planet, past the solar system. Because the emptiness doesn't stop at the atomic level. It goes all the way up. It echoes this emptiness at every scale. Let's talk about stars. Our sun is a star, and our sun is, by any reasonable human measure, enormous. 1,300,000 Earths would fit inside it. It's a monster. And yet, when you look at the night sky, you see thousands of stars, our sun's neighbors, cosmically speaking. and they look close together. They look like a neighborhood. They look like you could almost reach out and, given enough time, walk between them. Let me correct that impression with actual numbers. The nearest star to our sun is Alpha Centauri. It's about 4 1/3 light years away. A light year is the distance light travels in a year, and light moves at 300,000 kilometers per second, every second. In 1 year, light covers about 9.5 trillion kilometers, and our nearest stellar neighbor is 4.5 times that, about 40 trillion kilometers away. Now, let's scale this down to something sensible. Suppose our sun is a grapefruit, a small grapefruit sitting on a table in front of you. On this scale, the sun is a grapefruit. How far away is the nearest star? Also a grapefruit, roughly, but how far? About 2,000 kilometers away. 2,000 kilometers. That's roughly the distance from New York to Denver. One grapefruit in New York, another grapefruit in Denver. And between them, nothing. Some intergalactic dust and a few hydrogen atoms per cubic meter, but essentially nothing. That's what the galaxy looks like. 2 grapefruits with a continent between them. And there are 400 billion stars in the Milky Way. 400 billion. And they are all, every single one of them, separated by these absurd, yawning, almost theological distances of emptiness. The Milky Way isn't a crowded city of stars. It's more like, imagine you took 400 billion grapefruits and scattered them randomly across the entire continent of North America. 1 grapefruit per average area, roughly the size of Colorado. That's how spread out they are. Now, the Milky Way looks bright and dense when you see it on a clear night. That beautiful smear of light across the sky. And you know why it looks bright and dense? Because there are 400 billion of them, and your eye has no way to perceive the distances between them. You're seeing the projected light stacked up, collapsed into 2 dimensions from your point of view. It's a projection trick. It's an illusion of crowding. The actual volume of the Milky Way galaxy, when you calculate the fraction of it occupied by stars, actual physical stellar material, is so small that it staggers you. If you took all the stars in the Milky Way and redistributed them evenly through the galaxy's volume, the average distance between stellar surfaces would be mind-boggling. The fraction of the galaxy's volume that is actually occupied by stars is something like 10 to the minus 20. That's a decimal point followed by 19 zeros and then a 1. The galaxy, friends, is empty. That's the reality check. The thing we call the Milky Way, this vast, beautiful pinwheel of light, is almost entirely nothing. It is a structure made primarily of the absence of things. And we're just getting warmed up. Let's go bigger. Between galaxies, between the Milky Way and our nearest large galactic neighbor, Andromeda, there is even more emptiness. Andromeda is about 2.5 million light years away. The Milky Way itself is only 100,000 light years across. So the gap between us and Andromeda is 25 times the width of our entire galaxy. 25 of our galaxies could fit in the space between us, and there's almost nothing in that space. Some dwarf galaxies, some scattered stars, mostly vacuum. And when you zoom all the way out, as far as our instruments can see, you find the most extraordinary thing. The universe, at the very largest scales, is structured like a cosmic web. There are filaments, long, thin threads of galaxies and dark matter stretched across hundreds of millions of light years, intersecting at dense nodes called galaxy clusters. And between these filaments, voids, enormous, almost featureless voids, cosmic bubbles of near nothingness, some of them 300 million light years across. There's one called the Boerter's void. Sometimes people call it the Great Nothing. It's a roughly spherical region of space about 300 million light years in diameter. And it is, relative to the average density of the universe, almost completely empty. If the Milky Way were at the center of the Boerter's void, we might not have discovered that other galaxies existed at all until we had very powerful modern telescopes, because the nearest galactic neighbors would be so far away. Our own galaxy, by the way, sits on the edge of a void called the local void, about 200 million light years across. We're not in the dense heart of the cosmic web. We're on the outskirts, on the edge of a great emptiness, and our galactic neighborhood is being pushed away from that void. The emptiness behind us is actually helping to drive our motion through the cosmos at almost 1 million kilometers per hour. So here's what I want you to hold in your mind now. Hold the whole picture at once, because this is important. You are made of atoms. Those atoms are mostly empty space. Tiny, dense nuclei surrounded by vast electron clouds that are themselves mostly space. Your body, for all its apparent solidity, is an arrangement of nearly nothingness held together by electromagnetic forces and quantum rules. You are living on a planet orbiting a star. That star is one of 400 billion in our galaxy. The galaxy itself is, in terms of the fraction of its volume occupied by any actual stuff, almost entirely vacuum. Stars separated by distances so vast that if the sun were a grapefruit, the nearest neighbor grapefruit would be in another state. That galaxy is one of hundreds of billions of galaxies in the observable universe. The galaxies are strung along filaments, and between the filaments are voids, regions of space where, over hundreds of millions of light years, almost nothing exists. And yet, and this is the part that I find the most extraordinary, you feel solid, you feel real, you feel present, and the rock is hard, and the chair is firm, and your heart is beating, and it all seems so substantial and reliable and there. The universe has pulled off the most spectacular illusion imaginable. It is built from almost nothing, from emptiness structured by forces and ruled by quantum laws, something that feels like everything. Now, some people, when they hear this, they get a little existentially uneasy. They say, so nothing is real, nothing is solid, everything is an illusion, and I want to push back on that because I think it's the wrong lesson. The lesson is not that things aren't real. The lesson is that real is more interesting than we thought. What makes you solid is not that there's a dense packing of matter. What makes you solid is the behavior of the fields, the electromagnetic repulsion between electron clouds, the quantum principles governing how particles can and cannot share space. Solidity is a behavior. Hardness is a consequence of forces. Reality is relational. It emerges from interactions, not from things simply being there in a solid classical sense. And this is why I love physics. Not because it takes the wonder away, but because it reveals that the wonder goes all the way down and all the way up simultaneously. Think about Rutherford back in 1909, when he and his colleagues shot alpha particles at a thin sheet of gold foil. They expected the particles to plow straight through, just deflect slightly, because the Thomson model of the atom, the plum pudding model, said the positive charge was spread out uniformly. Instead, most particles went straight through, but some, a tiny fraction, bounced straight back. Rutherford said it was as if you fired artillery shells at tissue paper and they came back and hit you. And what that meant, what that told him, was that most of the atom was empty and almost all of the mass was concentrated in a tiny, unbelievably dense nucleus. He had discovered the emptiness from the inside out. He fired things at atoms to find the holes. And what's beautiful about this, what I want you to appreciate, is that this didn't diminish atoms. It made them more extraordinary, a thing that is mostly space, and yet has such precise structure, such specific rules governing how that space is organized that it builds everything. Water, stone, DNA, thought, stars, all from the careful, lawful arrangement of almost nothing. Let me give you one more scale to think about. Let's go in the other direction, below the atom. Inside the nucleus, that tiny marble in our stadium analogy, you have protons and neutrons. And inside them, you have quarks. Quarks are bound together by the strong force, held in a space that is extraordinarily small. Now, here's a curious thing. Most of the mass of a proton doesn't come from the quarks themselves. The quarks account for only a small fraction of the proton's mass. Most of it comes from the energy of the strong force field binding them together. Energy has mass by Einstein's famous equation. So even the nucleus, which we're calling the solid part, is itself mostly energy, mostly field, mostly the dynamic activity of forces in a tiny region of space. So when you work backwards from your sense of solid reality, you find force fields, quantum probability waves, energy gradients, rules, patterns, information, almost. The most solid thing in the universe, when you look closely enough, turns out to be a set of relationships. Now, doesn't that make you want to know more? Doesn't that make you want to ask, what is a field, really? What is energy? Why do these quantum rules hold? Why does the strong force have exactly the strength it has? Because if it were even slightly different, protons wouldn't bind, nuclei wouldn't form, there would be no atoms, and there would be no universe, at least not one with any complex structure in it. That's the frontier. That's where we don't know. And I think not knowing is wonderful. I think the fact that we can ask these questions and sometimes answer them, and always find deeper questions hiding underneath the answers, that is one of the most remarkable things about being alive. I am a universe of atoms, little parcels of almost nothing, dancing according to quantum rules, held together by forces we understand more every year, sitting on a small rock, orbiting an ordinary star, in a galaxy that is almost entirely empty, in a universe that is dominated by vast, dark, silent voids. And I find that to be not frightening, but magnificent. Because here's the thing, the emptiness doesn't mean nothing matters. It means that what does exist, the thin threads of filaments where galaxies cluster, the brief moment of life on a rocky planet, the specific arrangement of atoms that allows you to read these words and understand them and feel something about them. These things are astonishingly improbable, astonishingly specific, and in all that vast emptiness, they exist anyway. You exist anyway. The galaxy is mostly empty. Matter is mostly space. And yet here we are, asking questions. That's the reality check. And I think if you really let it in, it's not a check that deflates you. It's one that expands you, if you let it. Because it turns out reality isn't less than you thought. It's far, far stranger, and far, far more interesting than you thought. And the more you look, the emptier it gets, and the more extraordinary the looking becomes. Thank you.